Good evening, everyone. Welcome back to our webinar series on quantum algorithms using Qniverse. Last week, we had with us Professor Anirban Pathak, who walked us through quantum veto protocol, which is a real-world quantum protocol through hands-on through Qniverse platform. So before we move on to this week session, I have a few quick announcements. The first one is on the attendance. Many are asking how the attendance will be recorded. For those who are joining through our webinar, the WebEx platform, for them the attendance will be taken care. You don't have to, put any fill up any form as such. For if in any case if you miss one of the sessions, you can watch our video, which will be the recorded session through our YouTube channel, that is Qniverse.in. And within 24 hours from the webinar gets over, the session gets over, the until tomorrow, you can watch the video, and you can fill up a form which will be given in the description to mark your attendance. Regarding the quizzes, we will be posting a short quiz after the webinar series, after the every session, through our different channels. It can be Zulip channel or the GitHub, and even now we have started our own WhatsApp public channel. So through that you can attend. Then we, with all the requests from the participants, we have started a Qniverse WhatsApp public channel, so you can join to that channel. All the information are being put on the website. I'll share the screen. So on the Qniverse.in, there is a menu, webinar. Click on that. So here all the information will be posted. The next session, uh, and what will you gain, okay, and who are the speakers, and what are the different platforms available for the course material, for discussion, video recordings, okay, and FAQs. So you can use this uh, platform for getting the information. Then on the questions to the speaker, you can post the questions through our WebEx chat, so that at the end of the session we can ask the speaker about your questions. But keep the chat clean. So unnecessarily don't keep posting the messages. Whatever the questions you need to ask for the speaker, so please ask only those in the chat box. Then many were asking about the Qniverse credits. So for Qniverse credits, um, those interested participants, you can submit a video testimonial sharing your experience and feedback on the usage and capabilities of Qniverse platform. Selected video submissions will get a special opportunity to visit our quantum lab at C-DAC Bangalore, where they can witness and engage real quantum computing setup on the first hand. And selected video testimonials will get free 100 credits on Quniverse platform. Other than that, to purchase the credits, you can mail to quniverse@cdac.in, and we'll get back to you on more information. And for today's session, we have with us Mr. Harishankar, who is from C-DAC Bangalore. He is a dedicated quantum computing professional and a graduate from NIT Agartala. He is working with us for last 1.5 years as knowledge associate at C-DAC Bangalore. He has worked on research and implementation of various quantum algorithms like Shor's, QPE, and Grover search algorithm. And recently, he has even contributed on the academic research with a publication titled Deterministic Quantum Search for Arbitrary Initial Success Probabilities. which explores a novel approach to quantum search methodology. His experts lies at the intersection of theoretical quantum information and its practical application. So today we will be hearing from Hari on Deutsch-Jozsa algorithm, gives, which is one of the early quantum algorithm, which proved that quantum computing gives exponential speed up over classical computing. So over to you, Hari.
Okay, thank you, sir, for introduction. Now I will start with the Deutsch-Jozsa algorithm. So I will present my screen. So I hope my screen is visible to everyone.
Yes, Hari, continue.
Fine. So today I will be presenting about the Deutsch-Jozsa algorithm. This was one of the early algorithm which was provided and showed the quantum advantage. So I will be starting with the problem statement. So the problem statement, the particular problem that this algorithm is used to solve is this. Consider you have a boolean function which take n bit inputs and return a single bit output, and the cardinality of the function is promised to be either constant or balanced. So the objective of this problem or of this algorithm is to determine whether the given function is a constant function or balanced function. So the assumption here is it is always promised to be a constant or balanced function, and we don't know the internal working of the function, like how it is working. So if you want to solve this problem classically, so classically, to solve this problem, you need to try like at least half of the entire input spectrum to get to know the cardinality of a function. For example, suppose a function takes 8 input and returns a boolean output, whether 0 or 1. And if it is a balanced function, so you need to try at least five, one more than the half of the entire input range, to be sure whether the given function is a constant or balanced. Suppose if the function would be a constant, so up till four query or like four inputs, even if you get a particular same input for all the four, unless you try it for the fifth input, you cannot know whether the function is a constant or a balanced function. So generally, if the function takes n bit input, so you see the overall complexity or query complexity for classically solving this particular problem is 2 to the power n minus 1 plus 1, which is one more than the half of the entire input range. So the limitation is, as the size of input increases, the number of bits increases, the complexity of this classical approach varies exponentially. So that's, but we use Deutsch-Jozsa's algorithm. This particular algorithm gives exponential speed up as compared to the classical algorithm. And you, as you see, classically you required uh, 2 to the power n, or which is like exponential time complexity. But with the Deutsch-Jozsa's algorithm, you can get the result with just a single iteration. So I will be starting with the Deutsch-Jozsa algorithm. What is how the circuit works, and what are the internal mathematics and the internal working of the algorithm is. But before that, I would like to give a quick recap about some of the basic quantum gates, which whose property we will be using in this Deutsch-Jozsa algorithm. So first is like Hadamard gate. As you most of you would be aware of, like Hadamard gate, when applied on a basis state, it returns a superposition state, as you can see here. Okay. So when Hadamard is applied on any basis state, you get a superposition state. The most general superposition state for a single qubit is this ket plus and ket minus, which is equal superposition of ket 0 and ket 1. The only difference is the phase associated with ket 1. Here you see it is a plus, and here it is the other part, it is minus. Okay. So Hadamard is used to bring a basis state into a superposition state. And when a Hadamard gate is applied on some superposition state, there is a possibility of having interference. As you see, when the Hadamard is applied on ket plus, we get something like this, and the final output is ket 0 only. So here you see, depending upon the state on which the Hadamard is acting, we may get some output value for which which depends upon the interference that has been happened. So here, if you see here the ket one, and we have here ket minus one. So you see these two ket one have the different phase. So this results in destructive interference. Whereas for ket zero, we have a constructive interference, and addition when we add these two, we finally get the output state as ket zero. So one notable thing is for a property of Hadamard gate, it provides a superposition of the state on which it acts, and depending upon the phase of the states, interference can be happen, which could be constructive or destructive. Okay, so now let's dive deep into more properties of Hadamard gate. So let's move on. When we see here, we see Hadamard acting on multiple qubits state, so which is here 0 0. So generally we know when Hadamard acts on ket 0, we get ket plus. So here we get the tensor product of ket plus plus. So this is something our what we get as the output state. Similarly, if it acts on some other state, we get some output. So here you see, if you try to generalize the Hadamard operator on some general n qubit state x, so you see you will get something like this particular function. Okay, so the action of a Hadamard gate on any state x could be viewed using this particular equation. So from this, we can make out two output or two take observation. The first is, whenever Hadamard is applied on any state, we get a uniform superposition of all possible states. Here you see z is varying from 0 to 2 to the power n minus 1, which is the total number of states that could be presented by the given number of n qubits. Okay, so the one observation is, whenever Hadamard is applied, it gives us a uniform superposition of all possible states, which can be represented as by those qubits. And the other property of Hadamard, which we observe here, is whenever we see the output is 0, the state for the state 0, when z is 0, we see the entire term becomes 1. Okay, minus 1 to the power 0, so it will, like a resultant phase would be plus 1. So we see whenever it doesn't matter on which state Hadamard is acting, the phase associated with the ket 0 in the output will always be 0. Okay, so with this two, we have to remember these two key properties, which will later we will use in the Deutsch-Jozsa algorithm. And one other property for some C not gate, which is a control not gate, I would like to show its property, which will be useful for building the oracle in the Deutsch-Jozsa algorithm. I will later explain what is the oracle. So we see the option, the action of C naught as a XOR operator. So if suppose C naught is acting on a 2 qubit, so whatever the output of Q1 would be, or the target qubit would be equivalent to the XOR operation performed on Q0 and Q1. As you can see, we have a truth table for a C naught operator. Here you see the input control and the input target. Okay, so we have input control and input target. So it can have these four possibilities. So, and if we see or observe the output at the Q1 at here, so you see when this particular truth table represents a XOR operation, when both the bits are equal, the output is 0, and when both the inputs are different, the output is 1. Okay, so this property that a C naught can be used as OR operator, we will be using further in while building the circuit for Deutsch-Jozsa algorithm. So now let's dive into the Deutsch-Jozsa algorithm. First, this is the general circuit representation of a Deutsch-Jozsa algorithm. Here you see we have a two quantum register. One is of n bit and the other is of a single bit. And the other qubit is initialized with the ket1, whereas the first quantum register is initialized with the ket0. Like all the qubits in this particular register has a phase of ket0. Now when Hadamard is applied on both the register. So like I will later on explain. So these are the Hadamard. This representation is Hadamard applied on all the qubits, all the n qubits. Here Hadamard is applied on this ancilla qubit or ket1. Then we have something as oracle function. So generally the oracle function is given to us, and we don't know the internal working of it. We just know its input and output. So you see this oracle function takes two input, which is x and y, and returns the value x and f of x, XOR y, as an output. So this f of x is the function for whose cardinality we want to know. Initially, the problem was to know whether the given function is a constant or balanced. So the function that we are talking about is this function f of x. So, and later on, we again apply Hadamard on the first quantum relation and we measure. So this is the overall circuit representation of a Deutsch-Jozsa algorithm. I will explain one by one at each stage what happens and how we derive the output from this particular circuit. One thing complex is building the oracle is itself challenging. So we will see how we build this particular oracle as well. So you see at the initial state, at this point, which is represented by ket psi 0, we have the first quantum ratio as ket 0 and the second quantum ratio as ket 1. So this is the representation of the initial state of the system, which is the first quantum register in uniform in all the qubit in ket 0 and the second quantum register as a ket 1. So now we see we apply Hadamard operation on all the qubits present in the circuit. So we see after applying the Hadamard is applied on ket 0, and one of the Hadamard is acting on the second quantum register, which is in state ket 1. So this can be represented. We already saw earlier that the action of Hadamard on any state could be represented by this particular equation. And since here the input is 0, we don't have the phase associated with any of the output state. And this Hadamard acting on ket1, we have already seen this is represented as ket minus, which if we expand, it is represented by this. So we know what would be the state at this particular level of the circuit. So now the first quantum register is in uniform superposition of all possible states, and the second quantum register is in the state ket minus. So let's see how the oracle works. We see the oracle takes input as x and gives the output as x as it is, and the second input on y, which is ket minus, it will have a XOR with f of x. So we see the representation, or after applying the oracle, we get this state. We see the first input, which is ket x, is as it is, and the second input, which is y, or like ket minus in this case, has f of x XOR with ket minus. Okay, so one thing is this particular block, f of x XOR ket minus, it could be represented as minus 1 to the power f of x into ket minus. This we see as, if suppose f of x is 0, then this particular entire value would be 1. And again, f of x XOR, if f of x is 0, then 0 XOR any value. This is the property of XOR operation, logical XOR operation, that any value when XOR with 0 returns the same value. And if suppose f of x is 1, then we get the entire thing as minus 1, which is minus ket minus. So for that, if we expand ket minus and put f of x as 1, we see we get something like this. And if we simplify, 1 XOR 0 is 1, and 1 XOR 1 is 0. So it will be exactly minus of ket minus. So hence we can write this entire thing, f of x XOR ket minus, as minus 1 to the power f of x of ket minus. Okay, so now suppose if the given function is a constant function, so what happens, this minus 1 to the power f of x, since f of x is a constant for all the values of x, it will have the same value. So whatever the value is associated, suppose it's a 1 or minus 1, we can take it out of the summation value, and we just remain with this thing. Okay, sorry. So we just have this particular value, and if we see this particular thing, it represents our initial state when Hadamard is applied. Okay, So this equation represents Hadamard applied on ket 0, tensor product with Hadamard applied on ket 1. So we can, this particular state after the oracle, at this point, if the function is constant, then we have here x as it is and y as it is, and all with the phase of -1 to the power f of x. Okay, so here it is. So we can write the stage f psi 2, which is after the oracle. This is the phase that we took common out of the summation, and this entire thing, h applied on ket 0 and h applied on ket 1 is same as the input. So now if the function is constant, later we see after the oracle, we apply the Hadamard operator only on the first quantum register. So the first quantum, if we apply the first quantum register, uh, Hadamard, so it is will be equivalent to applying Hadamard at this particular position, which is this. And we see after the after the application of Hadamard gate, after the oracle, we have something like this. So H, then again, this is the input stage, this. And as we see, Hadamard is only applied on the first quantum register. So we already know that Hadamard is self-inverse. Like if you multiply Hadamard with apply a Hadamard operator on some qubit, and then again apply Hadamard, so it would act as an identity. So this two Hadamard act as identity, and we get the first quantum register that we measure. We see we only measure the first quantum register, right? So if we measure at this point, these two becomes identity, and if we measure just the first quantum register, we would get the output as all the qubits in state 0. Okay, so this is the, when we measure the, we cannot measure the phase. So whatever the value of -1 to the power f of x be, the state of the qubits in the first quantum register would always be at 0. Okay, and now let's move on and see like what happens if the function is balanced. So if the function is balanced, we have f of x is 0 for half the inputs and 1 for the other half. So since f of x here is different, we cannot take it out of the summation. Okay, one thing is here we observe uh, the -1 to the power f of x, this particular phase came because we XORed get minus with f of x. So this term is, the particular term for this is phase kickback, wherein even the phase associated with one quantum register, it is now added to this particular first quantum register. Okay, so this particular thing is called phase kickback, wherein the phase from one quantum register jumps onto other quantum register. So since we cannot take the -1 out of this summation, because it may be +1 and -1 depending upon the f of x, and here f of x is balanced, so it can be 0 or 1. So in this case, let's, for the intuition purpose, we expand this summation and we can write it as a -1 to the power f of 0, ket 0, and so on. Like uniform superposition of all possible state, which is 0, 1, 2, and so on till the last state, and each associated with their phase of -1 to the power f of that particular state. Okay, so let's see what happens after. This is the state after the oracle is applied for balance function. So now we apply Hadamard on the first quantum register, which is equivalent to applying Hadamard. We see the second quantum register or ancilla qubit is in ket minus only, and the first quantum register is in uniform superposition with their phase. And now if we apply Hadamard, the Hadamard would be applied on each of the state after the oracle, which is this. So now if we apply Hadamard on each of the qubit, you see, earlier we read a property about or observed a property of Hadamard, that irrespective of what state Hadamard is acting on, we would always get ket 0 with a phase of 0. So now if we just calculate the amplitude of ket 0 for all of the state, so here we get the ket 0, when a Hadamard is applied, we get a uniform superposition of all possible states, but we just have to observe the amplitude of a ket 0. So if we take the amplitude of ket 0 from here, it would be -1 to the power f of 0. Then if we take the amplitude of ket 0 from here, it would be minus 1 to the power f of 1 into 1, 1 by 2 to the power n, and that's how we, for all the state, when Hadamard is applied, we get the amplitude as the summation of minus 1 to the power f of x. Note, this amplitude is only for ket 0. We are not observing the amplitude of other states. So if the function is balanced, we get the amplitude of ket 0 as this. So this particular amplitude is like nothing but this 1 by under root to the power n we already had. And when Hadamard is applied, you have observed earlier that Hadamard also introduces 1 by 2 to the power n. So the overall constant out of the summation would be 1 by 2 to the power n, and the summation of minus 1 to the power f of x. Okay, so since f of x is a balanced function, for 50% of input, f of x would be 0, and this overall value would be plus 1. And for 50%, f of x would be 1, so the overall value would be minus 1. And since we have equal number of 1 and minus 1 in the summation, the overall amplitude of ket 0 would be 0. So in this case, when the function is balanced, the probability of measuring ket 0 on all the qubit, or like all the qubit in state 0, comes out to be 0. So in conclusion, earlier we saw that if the function is constant, we measure the ket 0 with 100% probability, and if the function is balanced, we measure ket 0 with zero probability. So we cannot measure ket 0 at the end of the algorithm if the function is a balanced function. So in conclusion, we can say that after applying Deutsch-Jozsa algorithm, if at this point, when we measure the first qubit, if we measure all the qubits in ket 0, the given function f of x is a constant function. And if we measure the qubit in anything other than 0, like even it can be any state, we are not concerned about the state. The only thing we concerned or we looked was the amplitude of ket 0. So at this point, if we measure anything other than 0 on all the qubits, then we conclude that the given function is a balanced function. So this is the conclusion for Deutsch-Jozsa's algorithm. Okay, so one thing is how we build this particular oracle. Okay, so in most of the quantum algorithm, building the oracle is itself challenging. So Quniverse provides this entire algorithm on its own. So you can visit Quniverse, and you can. So on the Quniverse, you can log in and go to the algorithm section. I have already saved my credentials here, so I will be able to log in. So here in the algorithm sections, you can go, and on the top only you would find the Deutsch-Jozsa's algorithm. So you see this function is a many to one function or a boolean function which takes n bit, and it determines whether the function is constant or balanced. Okay, so for Qniverse provides advantage that we don't have to build the oracle on our own. Oracle is already implemented. So first we select the number of qubit. So suppose we select a 4 qubit, and we have option to select whether the function is constant or balanced. So suppose we have here three options. Already three oracle has been implemented. So f of x is 0 or 1. These two represents a constant function, and f of x equals to x1 XOR x2. That is the XOR of all the qubits present is a balanced function. So if I load the circuit, I will be able to get the Deutsch-Jozsa's algorithm. And you see the first quantum register, we selected 4 qubits, right? So these 4 qubits are the first quantum register. And the next quantum register, which was our ancilla qubit, which was initialized in 1. So this particular NOT gate is used to initialize that particular qubit in ket 1 state. And now we see this particular operator here. This represents our oracle. So I will later explain like why this is the oracle for balance function. In the meantime, we can submit this job and get the result. We know that this we have choose the balance function. So our output should not contain ket 0 state. So suppose we select a QPU hardware. So let's see which all backends are available for now. Okay. So generally this take time. So that's why I'm submitting the job beforehand only to get the result later on. So by the time I explain why this oracle represents a balance function, I will the we will get the job running and we will be able to see the result. So one thing is we have already seen that the C naught acts as a XOR operation. So here at this point, in the circuit, we see we will have the output as get 0 XOR with get 4. Then at this point, then again after this, at this point we already had the first input as cat 0 XOR cat 4, and now we have the control as cat 1. So now the output of here it would be cat 0 XOR cat 1 XOR cat 4. And similarly, if at the end of the similarly at the end at this particular point, we will have the output as cat 0 XOR cat 1 XOR cat 2 XOR cat 3 and XOR with 4 cat 4. So we have already seen the output at this particular stage would be cat 4 is cat minus XOR with, remember we have choose the function as the XOR of each bit, which was like f of x equals to x1 XOR x2 XOR x3. So here the output would be cat 4, which is cat minus XOR with f of x, which was Q0 XOR with Q1 XOR with Q2 XOR with Q3. So you see we have the output as we have desired, and the oracle is pre-built for us. So one thing is why this function Q1 XOR Q2 XOR Q3 or X1 XOR X2 XOR X3 gives a balance function. So you see when we have a uniform superposition of all possible states. Suppose in this case it is 16. So out of all the 16 states, if you make a combination, so it will range from 0000 to 1111. So if you have all this combination, you will observe in exactly half or exactly eh, eight values, you have even number of one, or and in exactly eight output, you will have a odd number of ones in the bit representation. So like in 000 we have 0 1. So if you see like 50% of time odd number of this would be activated, and 50% time like even number of this would be activated. So if it is even number of this is activated, we have no bit flip here, and if it is odd number, we have one XOR with the cat 4, which is a representation of a balance function. So I think the result would have been executed. So we can see the result here. So we see actually it ran on hardware, and since we have selected a balance function, the output which we desired, we measure cat 1111 with 100% probability. So we make the outcome. We did not measure cat 0 at the end. So we conclude that the given function was a balance function. Similarly, if you choose a constant function here in the algorithm section, suppose for the same 4 qubit, I select 4 qubit and I select a constant function, suppose for f of x equals to 1. So if we load the circuit, we will be getting the output. And this is the representation of a constant function. And if we run this, so we should measure get 0 with 100% probability. So let's see if we run. Let us get the available backends which are available. We can select a number of among a number of hardware available. So suppose we choose this regity, and let's wait to get the job confirmation. We get the job, and if we see, we chose a constant function. So when the output is get 0 on all the qubits with 100% probability. So with this, we conclude that the given function is a balanced constant function. So one thing is we can, in the Qniverse we have some set of constant and balance function. So if you want, you can, or there are other balance function also available. So if you want, you can come up with your own logic and build your own oracle logic to have a balance function. So with this, we conclude that Deutsch-Jozsa's algorithm is able to find the cardinality of a given function, whether it is a constant or balance, in a constant time. We see the entire oracle is called only once in the circuit. So we see it is the complexity, or the query complexity is order of one, which is a constant query complexity. So we have exponential speed up as compared to the classical counterpart. And as well, we see with just the help of one single extra qubit, or one single extra qubit, we were able to get the result. So that's it. With this, I would like to wrap up with this session. So thank you, and I hope you all have understood this uh, Dushosha's algorithm. And if you have any doubt, you can ask in comment section. I will be happy to taking any questions.
Hi, Hari.
Okay.
Thank you for that wonderful insight of DJ algorithm. Uh, there are a couple of questions.
Okay.
One, Ms. Anitya Gupta, she asked how a qubit can be put into superposition using the Hadamard gate detecting emotions.
Detecting
Emotions.
emotions. Actually, generally, the quantum property of superposition is shown by the quantum particles, or so you need to have something as a something quantum particle to represent this position. Generally, one example I can give is for superposition, which is mostly accepted, is a qubit is a general representation of a photon. Suppose a photon is a quantum particle, and to get it in superposition, we can have we can consider if the cube photon has property of polarization. So one thing is we can consider the horizontal polarization as a ket 0, and the vertical polarization is ket 1. So if we want to put it in superposition, we can just rotate the angle of polarization, and that could be considered as a superposition. Based on motion, actually there has to be some quantum interaction or some action on the qubit, or to bring that in particular superposition.
Okay. The next question is by Anayat Bashir. If we use cloning mechanism for Hadamard gate, does we have a different forms of DJ computation?
Like a cloning mechanism for Hadamard, like if you are saying you want to clone the qubit state, so actually it is not possible, because we have something called as no cloning theorem, which prohibits, or we cannot copy a quantum state from one qubit to another qubit. So I don't think we can have this kind of thing.
Okay. The next question is by Tania Singh. Where we can find the use of this algorithm in real life problem or in industry, like where we are interested to find constant or balance functions.
Okay, so Deutsch-Jozsa's algorithm was developed a long time ago, and it actually don't have a much application in the external industrial field. But this algorithm was developed to show the quantum advantage that we have over the classical mechanism.
Uh, yeah, good, Hari. Hari, you showed the DJ algorithm with respect to some 2 or 4 qubits.
Yes.
Can you show us with the large number of qubits how the complex the circuit will be? And could
Okay.
you throw
Yes,
us
I can
light
show,
on that?
and I can uh, explain you what the circuit complexity would be.
Yes.
So let us go to Quniverse, and let us go to algorithm. So suppose here the maximum number of qubit which is allowed on Qniverse is 10. Actually, we didn't have don't have any limit on how many qubits we can show, but generally to limit, you can the circuit, as the input grows, you see the circuit becomes too large, so it would be a problem for user to visualize the entire circuit in the same frame or same screen frame. That's why we have limited it up till 10 qubit. And as you can see, initially when I selected of just 4 qubits, I had 4 hadamard and 4 control not gate, and then again 4 hadamard. and one extra not and hadamard on the ancilla qubit. So for each bit added input, for each input bit added, we observe we just need a few set of gates added. That is one hadamard and one C naught. So you can say the overall gates the required to simulate, or the overall gates required for this Deutsch-Jozsa algorithm is the order of n, where n is the number of qubits. So that's it. The order is n approximately. It is the order of n. Actually, if you count the exact number of gates, it would be 3n. Okay, it would be 3n plus 2 gates. So which is again sim order of n only.
So one can create their own oracle in
Yes,
the platform.
yes, exactly. Like you can come up with, we had one oracle. Of course, we have a number of balance function for a given number of input. So you can come up and implement your own logic of oracle. Suppose I can even show you one of the oracle logic, even if we check whether the given.
Hari, that would be better if you, show us a
Okay,
different example of
okay. Let me
oracle
get
setup.
a smaller circuit, or I can just clear the screen and I can manage the number of qubits.
Yeah.
Okay. So suppose I am taking again example of a 3 qubit. Remember, for a 3 qubit Deutsch algorithm, we require 4 qubit because we require one extra ancilla qubit. Okay, and we require only 3 classical ratio because we measure only the first 3 qubit. So generally, we initialize the first quantum register with Hadamard, and the final ancilla qubit with we have initialized it in cat1, and then we apply Hadamard on all the qubits. One thing I will do, I will just mark this and group this gate because I require this gate again. So I will just name it as according to me, suppose SUP, to bring the superposition, and I will add the description here. Okay, so as you can see, I have this custom gate in my gate palette here, soup. So again, we remember that we require after the oracle, we require this again, this three element. So I do not need to drag and drop it again. So now one other logic is a balance function representation. So one thing is a user can do to come up with a balance function if you have a all possible states of n qubits, which is like, suppose example in this case, we have from 000 to 111. So if you see the first bit would be 0 in exactly 50% of input, and would be 1 in exactly 50% of input, right? So this can be a representation of a balance function. So if I add and I apply the target on my fourth quantum bit or fourth qubit, you see 50%. Now at this particular stage, we have uniform superposition of from ket 000, whose decimal equivalent would be 0, and ket 111, whose decimal equivalent would be uh, okay, 7. So that's it. So in this, out of 8 inputs, 4 of them would be odd. So only for the 4 input, this particular qubit would be activated, because I'm saying 000 from 111. So this particular bit would be 1 in exactly 50% of input. So you see, this is a representation of a balance function. And if I add, again apply Hadamard or series of Hadamard, we already saw we have grouped this, and we know. So this is a Hadamard applied on 3 qubit. So since this is a balance function, we should get anything other than all zero. So if we just measure this last bit, okay, the first quantum register, and if we run on, suppose on CPU this time I'm running on, so we have a lot different simulators. So I have just kept it with the default setting, and I should get the job and the result. So okay, so it is taking time to run. Actually, in few seconds it should be done. So one thing is I can just in the probability distribution viewer here, since we have 4 qubit in the circuit, we have the probability distribution for all the 4 qubits, but we are measuring only the first three. So you see in both the outputs, the first 3 qubit is in the state. The first three, when I say actually the bottommost qubit, the Q3 is the first qubit here in the state representation. So when this is 0001, you see the bottommost qubit represents the bottommost bit in this graph. So you see we measure the output as the 001. In both the case, the top three registers are in state, top three qubits are is in state 001. So that is what we should get, and see we get 001 for 100% of time. So since this function was a balance, we did not measure the zero on all the qubits. So this is the one of the logic of implementing a balance function. If you want, you can implement like a mathematically you can find out the number of combinations a balance function can have. I will just say, if you say I will give you a number for a given n bit input, you can have n factorial divided by n by 2 factorial square different possible balance function. So you can come up with your own logic to implement Qniverse, and if you want, you can try out and make a video of it, and you can send us to us if you want. Okay, so I hope that this has answered your question.
Hari, the next question is by Annapurna. She is
Okay.
asking, what is the difference between quantum dot based works and qubit based works? Which is more efficient?
Okay, so the efficiency, it is actually on the hardware side, or like what is the logic for the computation thing. For now, like we are only working with the circuit-based thing, so I cannot exactly comment about the efficiency of these methods.
Okay. The next question is by Lakshmidhar. Can you please explain the real time use case of this algorithm?
Okay, so I think we have already answered this question. The real-time use case, actually, this is generally based on the finding the cardinality of a function, and we see actually this. The purpose for developing this algorithm was to demonstrate the quantum advantage.
Okay. The next question is by Vikas. Can we design DJ algorithm without using Ancilla?
So the answer would be yes. So suppose let me share my window.
Keep your screen shared. Do not
Okay.
stop
Okay,
sharing.
fine. So, first, I will go and explain it from the year. So, the overall objective of this ancilla qubit was to introduce a phase, or you say a phase kickback to the initial or the first quantum register, right? So this was the overall objective of the oracle in this particular problem. So if we omit the ancilla qubit, so then we need to have something like this particular wait. This particular oracle should take only one input and should give us x XOR f of x as an output. So, or like something minus 1 to the power f of x times x. So, this would be a phase based oracle. I like if you want, I can show you a phase based oracle that being here. If so, suppose we take the same logic and this time we uh, remove the ancilla qubit. Okay. So if we just remove the ancilla qubit, we have something same. We see the initialization and the initial state we have applied Hermat. At the end we have applied Hermat, and then measurement. We just now need to come up with some oracle to measure whether the function is constant or balanced. So for the balance function representation, we can choose suppose S Z gate, which adds a phase of actually I should remove this, then you will be able to understand like better. So if we go to the state vector representation, now this is just a single representation of a balance function. So when you introduce a phase of z, so z gate has a property that it adds a phase of -1 only on the state 0. So if you see, we have a 3 qubit state, and we see phase of 1, which is like a angle of pi e to the power I pi. So you see, whenever the first qubit q0, we already saw like the rightmost bit is the uh, least significant bit, which is a q0, and so on. So you see, whenever this qubit is in state 1, we have a phase of 180 degree, which is equivalent to -1. So, and whenever the qubit is in state 0, we have the overall phase as get 0, overall phase as 0 degree or as 1. So this is a representation of a one kind of a balance function. And now if I apply again Hadamard, series of Hadamard and measurement, so superposition gate I have made. So we should, since this function was a balance, we should get anything other than 0. So that's what we get. We get the output as 0, 0, 1, which is the indication for the function is the given function is a balance function. So if you use a phase inducing oracle or the oracle which introduces a phase, so then you can have or solve Deutsch-Jozsa algorithm without using the ancilla qubit, and since and that's it. So
Yeah. The next question by Vikas himself, that can we run DJ for non-constant and non-balanced functions?
actually I was expecting this question early on. So one of the assumption of a Deutsch-Jozsa's algorithm is the given function has to be a constant or a balance function. So suppose when some black box is given and you don't know whether the function is a constant or balance, or it may be any kind of function. Suppose. So I will just apply some random gates, and you see this does not represent any constant or balance function because I have just randomly drag and drop. So I should get some kind of output. Okay. So suppose I have just some random gates or something like this. So this is neither a constant nor a balance function. So the Deutsch-Jozsa's output was, if we measure ket 0 with 100% probability, then it's a constant, and if we measure anything other than all 0, then it's a balance function. But in this case, we see like based on the oracle, yeah, I have just a drag some gates, and it's some random function. So you see, you have a probability of measuring ket 0, which is not 100%, neither 0%. So in this case, if you measure, and suppose you measure ket 0, you will be in the false assumption that the given function was constant, whereas it was neither of it. So, like in theoretically, after measurement, we get the state collapse. So, if you say in a theory, when the function is not a constant, neither a balance function, then you will have some non-zero probability of measuring get 0. Okay. So that's it.
Yeah. Uh, 1 second. Yeah. Next question is. Ah. Next question is by Rahul. What are the use cases for quantum computing? What will be its impact on today's TLS algorithm, like ECDSA or RSA encryption?
Okay, so quantum computing, like in quantum computing, already algorithm has been developed. One of the significant algorithm in quantum computing is Shor's algorithm, which was used which gives exponential speed up to find a factor of a given integer. So generally in RSA cryptography, the baseline difficulty for decrypting it is to find the factor. So generally Shor's algorithm is there, and you can have quantum algorithm, like even Grover's is used to search keys in AES methods. So it will definitely have effect and on the current algorithm, or encryption based algorithms, but works are already being carried out on post quantum cryptography, which is will give us like a cryptography algorithms which will exist in quantum era.
Okay. The next question is by Swastik. He is asking what the difference between the Grover search-based oracle and DJ uh, algorithm oracle.
Okay, so the DJ's algorithm oracle, it has the function was sure to be uh, the given function was boolean, and it was sure to be a constant or a balance function, whereas in Grover's algorithm, which we will be covering in the upcoming sessions, the oracle is, I will just give a gist of the oracle function. So there the oracle is again a boolean function, but it is not mandatory to be a constant or balance function. There the function just have to take care whether the target state or the state which we are searching for if the input is that particular state, then the function returns 1, and if it is anything other than the desired state or target state, the function outputs as 0. So this in detail we will be covering in upcoming Grover sessions, Grover's
Yeah.
algorithm section.
The next question is by Anand Babu. Let's assume I created one quantum circuit with 3 qubits, but only one classical register. What
Yes.
will happen for the above?
Okay, so generally, if you like here, you can see the probability distribution based on the whatever the qubit is. But once you run the circuit, and suppose I have just a single classical bit as this, so if I apply measurement, I can only apply measurement on measure only one of the qubit. It can be the Q0, Q1, or Q2 that I can select, but it will be any one. I can measure only one of the circuit, because after measuring, we do not get the result from the qubits. We get the result from the classical bit, like in which state the qubit collapsed. Okay, so if you don't measure the other two qubit, suppose in this case Q0 and Q2, if they are in superposition, and if you do not measure, they will remain in superposition. Whereas in Q1, as soon as you measure, it states gets collapsed, and you will measure output. If you run, you will get the output for only a single classical bit that we can submit. By the time the job is getting executed, we will take other questions.
Yeah. Next question is by Vipin. He asked, from an experimental perspective, what are the main technical challenges in implementing DJ algorithm for higher values of n? Have there been any significant breakthroughs in overcoming decoherence or gate errors for this algorithm, especially as circuit depth increases?
So actually, the if you want to overcome once the circuit you have, one thing is you have to take in consideration is the Oracle implementation. The Oracle implementation in the Qniverse, it takes some order of n gates, but if it varies according to problem or what kind of function is given to us, and currently right now we do not have any actual QPU which is fully noise aware, or like which has a 100% accuracy. So as the depth increase, definitely we would have like less accurate result.
Yeah. The next question is by Bhaskar. He asked how to get phase and amplitude coherence using this DJ algorithm.
How to get phase and amplitude coherence? So like one thing is in the quantum property, like whenever you measure in currently the quantum computation are based on Z basis measurement. So whenever you measure, you cannot measure the phase. So suppose if I clear the circuit and I just have a Adamad and a phase gate here, and so if I just see the state vector, we have a phase associated with the state one. If I reduce the other two qubits, so you see the cat 0 is having the phase angle of 0, and cat 1 is having the phase angle of 90-degree. But if you measure this, so sorry, this is the measurement. If you measure and if you run the circuit, you will only get either cat 0 or cat 1. So
Okay. The next question is by Annapurna. She is asking how she can develop her own algorithms in Qniverse.
okay, so you can use Qniverse to develop your own algorithms. Okay, so of course, you have to come with your logic, and you can like of course play with gates here and see what is the action of each gate, and if you get some insights, you can create your own algorithm here with the drag and drop composer. We even have we even support this code-based development of algorithms. Here you can write your Qiskit code or a Circ or whatever in whatever framework you are comfortable with. You can use and come up or develop your own algorithms.
The next question is by Apurva. She asked how to perform a forensics operation on the quantum instruments. How does that process happen? Is quantum forensics applicable to this set of algorithms?
Okay, so like a forensics on this set of algorithm. Like I don't know. I'm not completely aware. Getting what she about to ask. She wanted to ask, but the
Yeah,
application of
maybe
quantum.
the set of application what the DJ or any other D algorithm, Deutsch
So
algorithm.
actually, in forensics, if we want to use actually in biochemistry, there are applications of quantum algorithms. Like we have Bayesian algorithms and optimization algorithms, which predicts or gives drugs discovery or other things that we have many applications in biochemistry and even normal chemistry of structure prediction or material sciences.
Hari, Shore's algorithm can be used for quantum for I mean forensics.
Shows no. Generally, shows is a very dedicated and is it generally used to find the factor of a given number. So generally it has a very specific application. If someone comes up with some kind of logic of mapping forensics problem to finding the factors, then that can be used. But other
Okay,
than that, shows itself cannot use for any other purpose.
okay. The next question is by Mukesh. Can we still apply this algorithm if the function is not balanced or constant? I think you
Okay.
have answered
Yes,
to
I
this
have
question.
already answered this.
Yes.
So
Then we'll go to the next question. This is a very basic question. The Dr. Chandrasekhar, he has told that he wanted to know if the qubit is in a mixed state, that is 50-50 percent. But when we measure, it collapses to 0 or 1. How
yes.
is it? So can you
So
just explain it for him again?
when the qubit is in superposition and when we measure, it gets collapsed. So
Yes.
actually, this is the property of quantum particles or quantum mechanics itself. Anything, you might have heard the famous Schrödinger's cat theory that if you put a radioactive material in a cat in a box, so unless you open the box, the cat is both alive and that at the same time. But as soon as you open, you will definitely know the state. So that's how it works, quantum superposition. Unless there is some observer, it can be in any state. We cannot predict. We cannot even predict whether it was in a fixed state or it was in some superposition state. But once we observe, it is sure to be in a fixed state, whether it is get zero or get one.
Okay. The next question is by Rohini. Is Qiskit can be used for developing solutions? I think definitely we have the
Very
Qiskit
simple, I think.
framework in our Quniverse platform also. So
Yes,
you
we
can
have.
use
I can show
Qiskit.
you. We support different frameworks I hope this is visible that Cascade, Circ, CodaQ, Quest, QLAX. So we have multiple frameworks available and Qniverse supports it. So with whichever framework you are comfortable with, you can use that framework and go to develop your own quantum algorithms.
Yeah, Dibya Jyoti Sahu, she asked, in Quniverse, we have this state vector and probability distribution graphs, which
Yes,
is being shown on the left-hand side corner. Uh, so there itself, we can see the output of the qubits,
yes.
which are in which state. So why do we need to run the code? Is it just to verify it?
So actually, one thing is
Actually, to answer to this question, I'll answer. So this is the ideal probability which you are seeing, and it is only for maximum of 6 qubits. So beyond 6 qubits, you have to run to see the output, and this is only ideal. So if you say an Hadamard gate, gives you an ideal probability of 50% and 50%. But when you actually run, it is not exactly 50%.
So, it is again probabilistic, and
Yes.
suppose you apply Hadamard on a simple state and you measure. So if you repeat this experiment, suppose two times, so ideal probability should give you one time get zero and one time get one because it has 50% probability. But that is not the case. You might get both the time get zero or both the time get one.
Yeah. Next question is by Priyanshu. He is asking, can you suggest any resources? So he'll be starting his masters in physics this year, it seems. So he would like to know, is there any resources which you can suggest so that he can explore as prerequisites to understand these sessions better?
So actually, like C-DAC Quniverse is itself developing a course on the quantum algorithms and from basic to advanced, like from what is a qubit and quantum properties of superposition, entanglement, and interference till advanced algorithms like QML applications. So you can use that. While it is being developed currently, but once it's developed, you can use that.
Okay. There is next question by Lalit. Is asking what's the time complexity for DJ algorithm for a large number of qubits, say for example 50 or 100.
So actually, if you say the query complexity, like how many times we need to call the function, oracle function, generally, whereas in classical you map it as a like a, if a given function is there and you want to know the time complexity, so generally you require like how many times this particular function is called. So in quantum, if you map the time complexity with how many time the function is called, then it would be O of one, or like it is O of one.
Okay. Yeah, the next question is by Sri Darshini. Why does the balance function always yield a non-zero state?
Okay, so actually, I think the question is not framed properly. The thing is, balance function always yields a zero state, not a non-zero state. Okay, so as we already see in the balance function, we have the phase of all the state as same. So there is no destructive interference, and we get the get zero as the output as it is, because all the states it gives gets on add to we get zero.
Okay. Yeah, that's all for this session. Thank you, Hari. Thanks for that insightful session and answering all the questions of the participants. It was great having you for this